Cobalt is one of the really important metals in the energy transition because it is needed in batteries. And batteries, of course, are something that we are going to need in increasing amount for electric vehicles and all the other lower carbon energy solutions.
Cobalt is used in many industry applications, but lithium batteries are the single most important use for cobalt in the modern society. The cathode in a lithium battery contains cobalt to stabilise the very flammable lithium. But cobalt is also an important component in magnets and in high strength and wear resistant metal alloys, or so-called superalloys. Extremely strong metal alloys are needed, for example, in the aerospace industry for construction of airplane turbines, or in the steel used to construct wind turbines and diamond drills. So cobalt is sort of a superhero of the metal world, making other metals stronger and more stable. But cobalt is also known for its characteristic blue color, and it is used as coloring in paints, glass and ceramics.
But where does cobalt come from? In this short video, I'll explore global production and mining of cobalt and summarize the main geological environments in which cobalt ores are found.
The energy transition has meant that the demand for cobalt has been growing over the past few years. In many countries, cobalt is listed as a critical metal because of its importance for the economy and the risks associated with the cobalt supply chain. The Democratic Republic of Congo currently produces more than 60% of the world's cobalt. However, cobalt and other metal mining in Congo has long been problematic because of the history of conflicts in the country. In addition, a significant proportion of cobalt production in Congo arises from unregulated artisanal mining without appropriate environmental and work law practices, giving rise to many problems around serious issues such as child labour and environmental damage.
So there are many political uncertainties and problems surrounding global cobalt production, and this means that there are concerns about the security of supply for the metal. Research is currently going on into how we could reduce or maybe even completely eliminate need for cobalt in lithium-ion batteries, but at least for the time being, lithium-ion batteries do need at least some cobalt in order to provide stability. But let's now have a look at where in the geological environment cobalt actually comes from.
Cobalt is not rare in small amounts in almost any rock on Earth. There are many ore deposit types where cobalt is found in small amounts, but the most common deposit types for cobalt production are magmatic, lateritic and sedimentary basin deposits. In magmatic rocks, cobalt is most abundant in mafic and ultramafic rocks, together with metals such as nickel, platinum group metals, chromium and copper. The ore minerals are usually things like nickel sulfide pentlandite, but these minerals can incorporate quite a lot of cobalt within their crystal structure. That is why some mafic and ultramafic intrusion-hosted deposits can produce significant cobalt as a byproduct, such as the Bushveld PGE and chromium deposit in South Africa or the Norilsk nickel-copper PGE deposit in Russia. About 20% of cobalt globally comes from magmatic sulfide deposits.
But in most cases, to form a mineable deposit, either as a primary ore or a byproduct of some other metal production, you need to enrich the cobalt, so remove it from the original rock and deposit it somewhere else.
This can happen in two ways. One is the process of deep weathering of mafic and ultramafic rocks to form a soil type called laterite. Surface waters gradually weather the bedrock, enriching cobalt and nickel into mineable lateritic ore. There is a strong climatic control here. You can only get this type of deep weathering in tropical and subtropical regions, particularly those with alternate wet and dry periods. But only a relatively small portion of cobalt, about 15%, is mined from laterite deposits.
In most cases, the enrichment process requires hot hydrothermal fluids that are capable of extracting the cobalt from its original host rock and moving it somewhere else. And the most important cobalt-bearing ores of this type occur in sedimentary basins.
Sedimentary basins host so-called strata-bound ores, which are a key source for base metals. Particularly sedimentary copper ores often contain enough cobalt to be a valuable byproduct. Basin-hosted deposits of this type form when hot hydrothermal fluids within the basement rocks of an active rift basin mobilize metals out of the bedrock. The volumes of fluids involved in this process are huge, so they have a lot of potential to mobilize significant amounts of cobalt and other metals. These metal-bearing fluids then flow back towards the surface along the normal faults within the rift. The ores are deposited near the faults into the porosity of the basin sediments. Basin ore deposits are mostly within old sedimentary basins now caught up in ancient mountain belts, so they are typically highly deformed. Most of the Congolese cobalt-bearing copper deposits, as well as the cobalt-producing mines within the Zambian copper belt, are of this type. But other places have similar cobalt-bearing deposits too.
Another example of hydrothermal fluids enriching cobalt in sedimentary basin rocks is this one here. What I've got here is some drill core from the Rajapalat prospect in Finnish Lapland near Rovaniemi. Finland is currently the only country in the EU that has active cobalt mining, and there is potential for more.
This project is at an advanced development stage, so it's not actually a mine just yet, and the main product here in the potential future mine will be gold, but there is also significant amount of cobalt here.
Well, the rocks at Rajapalat are very old, almost 2 billion years old in fact, so they have gone through a lot of metamorphism and deformation. But they originally deposited as volcanic and clastic sediments into an ancient sedimentary basin.
It's not really known with certainty where the cobalt originates from in this case, but research so far suggests that the original mineralization here may well be of the basin-hosted type. So, the sediments were intruded by hydrothermal fluids carrying cobalt, sulfur and iron, and also some other metals like copper. The metallic minerals then precipitated from these fluids into the porosity of the sediments.
So Rajapalat is a good example of a cobalt mineralization that has been made possible by this enrichment process by the hydrothermal fluid activity in a sedimentary basin. Interestingly, at Rajapalat there's actually a second, much later fluid injection as well, and that one brought in some gold. If this prospect here is economic, it will be because of the gold and not because of the cobalt, and cobalt will, once more, be a byproduct.
But let's go somewhere completely different. I've come to Morocco to find out about a slightly different cobalt deposit type. As mentioned, cobalt is usually mined as a byproduct, meaning that the supply of cobalt is largely dependent on the demand for and economic feasibility of mining of these other metals.
But there are places in the world where it's actually making a primary ore. I've come to one of these places, to the Bou Azzer district in Morocco. Let's have a little bit of a look around as to what sort of mineralization we got here.
Morocco is the 9th biggest cobalt producer in the world, with about 1% share of the global production. The majority of the metal comes from the Bou Azzer district. There are several individual deposits in the area. Some of the smaller mines have been closed, but the bigger ones still operate, with the Managem Bou Azzer mine being by far the largest.
Unfortunately, we couldn't go into the mine itself. It's obviously a working mine, but there are bits and bobs of mineralization around here elsewhere, so let's go and have a little bit of a look around.
The Bou Azzer district is geologically part of the so-called Bou Azzer inlier, thrusted southwards onto older basement rocks.
The Bou Azzer inlier consists of ancient oceanic floor rocks, so mafic and ultramafic rocks, and they weather into these sorts of green landscape. But that's not actually where the ores are. The cobalt here, like in many cobalt mineralization worldwide, need to be reworked and enriched by secondary processes to really make the ore.
The old ocean floor rocks, particularly the serpentinites, do contain some cobalt, and the current understanding is that it's that cobalt that has been remobilized by hydrothermal fluids and deposited in hydrothermal veins and massive lenses within the serpentinite and surrounding rocks. This process happens long after the Bou Azzer inlier was already emplaced onto the basement rocks in its footwall. The favourable combinations of rock geochemistries, the compositions of the hydrothermal fluids, and the existence of suitable geological structures for the hydrothermal fluids to channel into, made this rare type of cobalt ore deposits possible. Many of the smaller mines in the area are now closed. One such mine was the Umel deposit, where I was shown around by Mustafa, who was a security guard at the mine. This particular mine, when in operation, reached almost 200 meters in depth. The ore here, like elsewhere in the Bou Azzer district, consisted mostly of the minerals cobaltite and scuterudite. After a good look around here and in the wider area, it's time to see what I found. So, back at base in the town of Agde, about an hour's drive east of Bou Azzer, I've collected some of the original serpentinites and other ancient ocean floor rocks, and I've also found some nice examples of cobalt mineralization.
So the cobalt has been leached from the serpentinite rocks and deposited in hydrothermal veins and massive lenses within the serpentinite and the surrounding rocks.
The veins and lenses contain many metallic minerals, with scuterudite and cobaltite being the most important ore minerals here. But there are also some rarer cobalt arsenate minerals, such as rosolite and erythrite. You only get deposits like this with very large volumes of hydrothermal fluids, which are essential for the enrichment process.
So you really need that enrichment process by hydrothermal fluids to make proper cobalt ore.
But whatever deposit type our cobalt comes from, two things are certain. We will continue to need cobalt and, like many other resources, it needs to be extracted responsibly and equitably, respecting the needs of both the local environment and the communities.